We are here for the subject of statistics, for which the principal investigator is Dr. Bhaswati Ganguly, Department of Statistics, Calcutta University. I have been entrusted with the task of preparing the topics on design of experiments and survey sampling. Altogether, we have 40 modules under this broad topic. These two subjects, design of experiments and survey sampling, are very basic courses in all undergraduate teaching statistics courses all over India. Also, in the postgraduate level, these two topics are taken up at an advanced level. So here we will be having a glimpse of the basic subject matters in these two topics, and then we will move to the courses which are taught usually in the university system. Moreover, these two topics have been so thoroughly discussed in the literature and so thoroughly used in real-life applications that we find that these two subjects are also covered in various service courses offered by the university statistics departments. So these are very basic, and then in this course we will be having an idea about the basic recapitulation of the concepts that are given in the undergraduate course. From there we will take up and go for the final thing. I am Professor Vikas Sinha, retired Professor of Statistics from Indian Statistical Institute, Calcutta. I have made a special effort to prepare these 40 modules in the form of a dialogue between the instructor and the student. I will be representing the instructor BKS. The full name is Bikram Kranti Sahai. And Moumita Chatterjee, she will assist me as being the student Sagorika Ghosh, abbreviated as SG. So all three you will find BKS and SG entering into a conversation, academic discourse in the two subject matters covering all the 40 modules. When we go from design of experiments to sample surveys, she might be replaced by some other student who will see what is coming up next. So with this basic background, let's look forward to a very exciting conversation in these basic areas of subject matters, and let us look for the module number 1. We start with a recapitulation of completely randomized design, abbreviated as CRD. I am sure you have a very clear understanding from your undergraduate studies of the models underlying CRDs, RBDs, and LSDs. These are the completely randomized designs, randomized block designs, and Latin squared designs. When I say you have a clear understanding about the models, I mean you must be knowing fixed effects, additive models with homoscedastic errors. That is how the models are written, with appropriate interpretation of the different terms that come up in the expression for the model.
Sir, we have studied one-way, two-way and three-way ANOVA models. I believe you are referring to those models. Yes, I know what ANOVA table means for each of these three classifications. For example...
Well, I presume you have a clear understanding of the models underlying these. As I said, I am referring to them. And then let us be serious and start from the beginning. I take up an example from Goose and Jones, 2011 book, page 79, table 1. This example illustrates many other aspects. For our purpose, we consider three suppliers of raw material to produce finished packages, and the measurable characteristic is the peel strength of the package, which measures the amount of force required to open the package. Here are the complete data sets. As you see in the table, there are three suppliers labeled as 1, 2, 3, and you see the records of the peel strength that shows supplier number 1 is giving the produce for 1, 2, 3, 4, 5, 6, 7 packages, and the peel strength of these 7 packages are written in suitable units as 4.36, 5.20, etc. Like that, we have the results under supplier 2 as well as under supplier 3. I hope you can see and feel the data now.
Yes, sir. I can even see formation of ANOVA table with two components of variation. The first one is between suppliers with V minus 1 is equal to 2 degrees of freedom, and the second one is within suppliers with N minus V is equal to 24 minus 3 is equal to 21 degrees of freedom, right? I mean, in general terms, there are V suppliers and the replication numbers are N1, N2 up to NV, where N is equal to summation Ni from I runs from 1 to V. That is, N is equal to the total number of observations.
That's very right. Let us talk about the errors in the model. As you may recall, these are assumed to be IID normal 0 sigma square. Therefore, the mean squared within MSW serves as an unbiased estimator for sigma square with n minus v degrees of freedom. One final point, this is known as one-way fixed effects additive model, abbreviated as FEAM. Do you realize that under normal errors, sample means and sample variances are the sufficient statistics? Therefore, instead of the complete data, we may be given only the abridged version of the entire data set, namely the table showing suppliers 1, 2, 3, sample sizes 7, 8, 9, the sum of the observations, etc., etc., sum of squares of the observations corrected, etc., etc., etc. This is called SS, sum of squares. Got it?
Yes, sir. And after this, the very next step is to perform F-test for the null hypothesis of equality of suppliers' effects. In case the hypothesis is rejected, we go for pairwise comparisons, and in this context, we discuss that about critical difference, Sheffe method of multiple comparison, and 2K method of multiple comparison. Am I correct, sir?
Okay. I can see that you have an idea about the sequence of data analysis steps and the inferential aspects involving one-way ANOVA model. In this context, I can refer to a very standard reference textbook, Sierra's book on linear statistical inference. At the master's level, that book you need for other topics as well. In that book, you will find a good treatise on this one-way ANOVA model. Let me ask you a quiz at this point. Based on my teaching experience over a number of years, I find this quiz very, very fascinating and challenging to the students. Imagine you are told, for some reason, the sum of squares of the observations corrected for data underlying the supplier number 3 is erroneous and hence should not be used. So you have the 3 suppliers. You have the table of the sufficient statistics, sample size, then sum and the sum of squares. Now we are told that the sum of squares corresponding to the supplier number 3, that is erroneous and that should not be used. However, we are still interested in the original hypothesis involving all the 3 supplier effects. Can you suggest a valid test in this changed scenario?
It's a bit tricky, I believe. My immediate thought would be concentrate on whatever is known for the other 2 suppliers and develop an F-test for the hypothesis of equality of the effects of supplier number 1 and 2 and ignoring the supplier number 3. That is pretty much straightforward, and I am sure that's not what you were looking for.
Naturally. Think it over.
If I look at the F ratio for the hypothesis involving all the 3 supplier effects, the numerator MSB for MS between is not affected at all since all the means are available anyway. That's because in usual notation, SS between is equal to summation of SI square by NI minus D square by N, where SI is equal to the total output for the ith supplier and D is the grand total for all the suppliers. I see a problem with the computation of SSW, which carries n minus v degrees of freedom.
Good. Your analysis is just right. You are on the right track. Now, how to go about it? I don't mind giving you another related quiz. Incidentally, this quiz is by itself interesting and highly revealing. This is the quiz number 2. You have data in a breezed table readily available for all the suppliers. You know the sum of squares and the sums. So everything is known to you and given to you. So that for the original hypothesis involving all the 3 supplier effects, there are altogether 7 valid F-tests. So look to the bold thing written here, 7 valid F-tests. Can you argue out?
7? You mean 2 to the power 3 minus 1? Oh yes, I got it. I got the answer to your previous question as well. I somehow missed the keyword valid. Now that you mentioned it explicitly, I can see the entire logic. Yes, it is very clear to me. It is pretty obvious to me now. I am sure you know what I mean.
I can see that you are very, very excited about it now. Yes, once you break up sum of squares W as a summation of within component variations and n minus v as summation ni minus 1 and realize that you are basically using the additive property of chi-square distribution in the formation of the denominator of the F ratio, the matter should be very clear to you. There are 3 sources for sum of squares within relating to the estimation of sigma square. You can use 1 at a time or 2 at a time or all 3 at a time. Accordingly, the degree of freedom will be calculated based on whatever data you are using, and each one will provide a valid estimate for error variance sigma square to be used in the denominator of the F ratio.
So when you say SSW for third supplier is not available, we can still use SSW1 plus SSW2, which carries N1 plus N2 minus 2 degrees of freedom, and the F ratio will carry 3 minus 1 is equal to 2 and 15 minus 2 is equal to 13 degrees of freedom. So the entire theory of one-way ANOVA is so much clear now. I have a related question for you. This is not really a question, more in the form of a query. The question is, why then we only study the F ratio based on maximum denominator degrees of freedom, that is n minus v, and do not take up or compute other F ratios?
Good point, Sagorika. Here comes the notion of power of F-test. There is a standard result which states that the power of the F-test increases with denominator degree of freedom. You are likely to learn this thing about the power property of the F ratio in your inference course in multivariate context. Anyway, so naturally, among the 2 cube minus 1 or 7 separate F ratios, the one mentioned in the ANOVA table, standard ANOVA table, that provides maximum power against any alternative because that carries n minus v degrees of freedom for the mean square W. Therefore, we are perfectly right in using it and nothing else in the formation of ANOVA table. But it would have been really desirable that there is at least a mention of this thing as a remark or note in the textbooks for the benefit of the readers. That indeed there are so many valid F-tests available for the same hypothesis is itself an amazing result. It seems pretty obvious now, isn't it?
So, once told, yes, it is very clear, but your quiz number 1 was puzzling indeed. What about a similar situation involving one of the sums or means instead of SS, that is sum of squares? Can we just work with the rest?
Good point. I was going to raise this issue anyway. I found this as a natural approach for introducing what are known as random effects models in ANOVA context. So let me take up some theoretical questions in this area. Question number 1. In the context of a CRD involving small n observations and V treatments with replications as usual n1, n2, nv, consider the two models. Model 1 tells the recorded observation Yij can be written as mu plus tau I plus Eij, and model 2 says that the same recorded observation Yij can be framed as mu I plus Eij. Usually these are the assumptions on the errors like IID homogeneous normal 0 sigma square. So the assumptions hold under both the models. Now you are supposed to show that the two models differ towards estimation of the model parameters. The two models provide identical data analysis for testing equality of the tau i's or of the mu i's in the two models respectively. And the third question is, can you identify parametric functions in both the models which possess identical estimates? So note that one model talks about Yij equal to mu plus tau I plus Eij. The other model talks about Yij equal to mu I plus Eij. Usually the interpretation given is, when you are writing mu plus tau I, you say mu is the general mean, tau I is the excess effect of the treatment on the top of the general mean. That is the interpretation of tau I in model 1. And in model 2, you say mu I is the total effect of the treatment I. That is how the two models are interpreted, the model parameters are interpreted, and these are the questions that you are supposed to take up. Another question is, argue that in the same framework as above, there are at the most 2 to the power v minus 1 valid f-tests for testing the hypothesis of equality of the tau i's or of the mu i's. And the third question is, show that in the same framework as question 1, the average variance of all pairwise estimated tau contrasts, as well as the generalized variance of the estimates of tau 1 minus tau 2, tau 1 minus tau 3, etc. up to tau 1 minus tau v in model 1, they will be the least when the replication numbers in i's are all equal or differ from one another by at most 1. But let me clarify this question number 3, which may look a bit difficult to you. First of all, you find out an expression for the variance of the pairwise estimated tau contrasts. Tau I hat minus tau j hat, what is the expression for the variance? And then you average it out over all pairs. That is the first part, getting an expression for the average variance. And then when we talk about generalized variance, we write down the dispersion matrix of the estimates of tau 1 minus tau 2, tau 1 minus tau 3, up to tau 1 minus tau v. Write down the dispersion matrix, take the determinant, that is what is called the generalized variance. So show that minimization of the average variance or minimization of the generalized variance by proper selection of the replication numbers n1, n2, nv, that amounts to the result which says that ni's should be all equal or they should differ from one another at most by 1. This is a theoretical exercise, quite interesting. The one on generalized variance is a bit tricky and a bit difficult, but I hope some of you can definitely get it through. Let me now ask Sagorika to read out the multiple choice questions.
So, question number 1 is, in an agricultural experiment, the experimental fields are located in 7 districts with likely local climatic variation across the districts. There is a collection of 33 fields altogether and 3 different variants of wheat have been produced.
You mean varieties of wheat?
Yes, sir. And yield data obtained. The data analyst carries out a CRD data analysis with between varieties degrees of freedom is equal to 2 and within varieties degrees of freedom is equal to 30. So the options are, the data analyst should test for normality before applying ANOVA F test. The second one is, the data analyst should apply one-way ANOVA F test since normality assumption is usually valid. And the third option is, one-way ANOVA F test should not be used since all the experimental fields are not likely to be homogeneous to start with. So this is the first question, and here is our second question. It so happened that in a completely randomized design setup, one particular treatment ended up with just single observation, while 4 others had more than one each. There were altogether 32 observations. So the options are: ANOVA F test cannot be performed since the experiment is out of control of the experimenter. The second one is ANOVA F test can be performed for the standard hypothesis of equality of all the 5 treatment effects, including the one with single observation. And the third one is F test can be performed excluding the treatment with a single observation, since this one does not have any reliable estimate and does not contribute to sum of squares within. So this is the second question, and here is the third question. In a completely randomized design setup, the experimenter started out with a total of 53 experimental units and 7 treatments. However, the treatment replicates, that is 5, 6, 6, 8, 8, 9, 11, could not be controlled by him. He then decided to provide extra units to those treatments with smaller replication numbers, and towards meeting his objective, he had received 19 additional units. He revised the replications as 12, 10, 10, 11, 9, 9, 11. So the options for him are: by doing so, the experimenter achieved least average variance of estimated treatment contrasts for a total of 72 units. The next one is: towards achieving least average variance of estimated treatment contrasts for a total of 72 units, he should have utilized 19 additional units respectively as 5, 4, 4, 3, 2, 1, 0. And the third one is: towards achieving least average variance of estimated treatment contrasts for a total of 72 units, he should have utilized 19 additional units respectively as 6, 4, 5, 3, 1, 0, 0.
Okay, so these multiple choice questions, they add up to your knowledge and understanding about the basic design CRD. You will find these quite entertaining and revealing. The question number 3, it borrows the idea from the minimization of average variance that we have talked about in question number 3 before, and the others are kind of a bit tricky. I would not mind discussing one question with you if you want to know how the thought process goes, getting the right answer to the MCQ. Okay, you can pick and choose.
Okay, so can you please give the solution of question number 1?
Okay, let's see what it says.
Yeah. Helpful for us. So, can I read out again?
Yes.
Okay, sir.
Go ahead.
The question was: in an agricultural experiment, the experimental fields are located in 7 districts with likely local climate variation across the districts. There is a collection of 33 fields altogether, and 3 different varieties of wheat have been produced and yield data are obtained. Now, the data analyst carries out a CRD data analysis with between varieties degrees of freedom is equal to 2 and within varieties degrees of freedom is equal to 30. So, the first option is the data analyst.
So, they have done a CRD analysis.
Yes, sir.
So, let's see what are the options.
The options are: the data analyst should test for normality before applying ANOVA F test. The second is the data analyst should apply one-way ANOVA F test since normality assumption is usually valid. And the third one is one-way ANOVA F test should not be used since all the experimental fields are not likely to be homogeneous to start with. So, what is the correct answer and why? That is my question. And if you can give this.
Yeah. So, if you read the text carefully, it says all these 33 experimental fields are located in 7 districts with likely local climatic variation across the districts. That means to start with, you cannot assume that all the experimental fields are uniform. They have uniform fertility gradient that you cannot assume. So in a CRD model, the basic principle lies on the fact that to start with, all the experimental units are uniform. They have got same quality. There is no quality variation unless you put the treatments, and the treatments make the variation among them. But here to start with, the experimental fields are already different in terms of climatic variation and its effect on the soil. Therefore, it is not within a CRD setup anymore. So the correct answer is number C. One-way ANOVA should not be used since all the experimental fields are not likely to be homogeneous to start with, in view of the fact that they are located in 7 different districts. So that is the correct answer is number C. Okay.
Thank you, sir.